All right, let's start lecture B now. Before we do that, let me just make a remark. Assuming you did it right, it's pretty amazing that you can take the derivative of something like that. Can you imagine taking the derivative of something like that with limits? With the limit definition of the derivative? No, and personally, I would not want to do it either. These derivative rules are pretty powerful. You can take the derivative of pretty much anything, any kind of ordinary function that you can think of. All right, again, our main topics for the rest of lecture B here include looking at partial derivatives again with compound interest again. Once again, looking at logarithmic differentiation, implicit differentiation, and then we'll also go back to thinking more about linear approximation. So these are technically all things you've seen before, but it's worthwhile to spend more time on it. I would suggest not writing what I'm about to show you down. In fact, while you're taking the quiz, I put this PowerPoint in the shared folder, okay? Just sit and listen, especially for this first slide. It's essentially something I've shown you already. The compound interest formula is this. I modified it from last Friday to make R be plugged in as a percent. And I even put a percent sign there. Of course, you don't actually do anything with the percent when you use the formula. So, for example, if R represents 4%, you plug a 4 in there, not a 0.04. If R is 8%, you plug an 8 in here, not a 0.08. The dividing by 100 takes care of the conversion to a decimal. If R is 8, 8 divided by 100 is 0.08. 8 hundredths. Why did I do that? I did it so that it's easier to interpret the derivative. That's why. That's a rate of change. Here are the four derivatives. And again, just think with me. And just look at these formulas and say, yeah, they make sense. If I was forced to do it and I was very careful, I could do it. Take the derivative with respect to p first. Pretend everything else is constant. That means this entire expression, complicated as it is a constant. Constant times p. The derivative of such a function is just the constant. Yeah. There's your Leibniz notation for the derivative, dA dp, or sometimes you'll hear people actually say partial a, partial p. The partial derivative of a with respect to p is probably the best way to say that. This notation you will see sometimes as well. Put a subscript under the function to emphasize what derivative you're taking. The partial derivative with respect to, in this case with respect to p. And yeah, you just get this constant, okay? Because we're thinking of everything else as a constant. Whether something's a variable or a constant is all in your thought process. What about the partial with respect to r? Treat the p, the n, and the t as constants. You got to recognize what kind of function that is. It's analogous to like 1 plus x to the 5th power or something. Analogous to that. Which means it's a polynomial, really, if you expanded this out. Or you can think of it as sort of a modified power function to the 5th power in this case. I mean, an actual power function would be just that. But this is just a slight modification by adding the 1. It's best not to expand it out. It's best to use the chain rule. Bring the 5 down in front, subtract 1 from the exponent, then multiply times the derivative of the inside, which for this function is just 1. But for this function, the derivative of the inside with respect to r is the constant multiple of r, which is 1 over 100 times n. So we get an extra factor of 1 over 100 times n. That's the chain rule. Notice I subtracted 1 from the exponent, and I kept the p there this time. I didn't make a mistake. This would be the answer. Think of it as a function of r, if you like. Okay? That's the derivative with respect to r. You can change your perspective. By the way, you can go back to saying, hey, everything's a variable once you've taken the derivative. And in fact, we're going to do that in Mathematica. But while you take the derivative, you think of r as the only variable. The derivative with respect to n is the hardest. Let's do with respect to t. Treat everything else except the t as a variable. It's an exponential function of t. The variable is now in the exponent. So a natural log will become involved. You do not subtract 1 from the exponent here. You need the chain rule ultimately to take the derivative of that with respect to t. That's the inside function right there, n times t. We'll get an extra factor of n right there after differentiation. Notice I have the log of the base. This is p times the natural log of this thing times this thing times n. It's all multiplications here. Okay? So it's more complicated, but it's doable if you're really careful. If it helps, you can use new letters. You can say let b equal 1 plus r over n, because that'll simplify the way the formula looks. Then the formula will just be pb to the nt. Differentiate that with respect to t. It's easier to see what the answer is. P, natural log of b, b to the nt, times n. Same thing as I got on the screen, except go back to 1 plus r over 100n for the b. Partial with respect to n again is the hardest. You have to use logarithmic differentiation. Now we did that last time. I made some mistakes as I was doing it. I did fix the mistake in the video, the mistakes by putting the notes at the top of the video. Before we do this, let's do a simpler example. Let y equal f of x equal x to the x. There's a simpler example of a weird kind of function where the variable is both in the base and the exponent. The variable is both the base and the exponent. How do you take the derivative of something like that? That's this technique of logarithmic differentiation. You take the log of both sides first before differentiating. If I take the natural log, and you want to use natural log, of both sides, I get this. And I'm just ignoring the f of x. For a moment. I could have put it in there. Then, before you differentiate, it's also good to use a property of logarithms. In this case, the property that you can bring that x out in front. Property of logs. Now differentiate. Go back to ordinary d's here because I'm not thinking about multivariable calculus. Differentiate both sides with respect to x. The right side's easy. Should be easy. It's the product rule. In fact, this was the question from lecture A, part of last Friday's quiz. This one, well, you might say, isn't that easy too? Isn't the answer 0? And no, it's not 0. Because y depends on x. It's a function of x. If you prefer, maybe I should have kept the f of x in there. If you prefer, you can write it as natural log of f of x. And there it's more clear that we need the chain rule. We have an inside function, f of x. We have an outside function, natural log of x. Derivative of natural log. Hang with me, I see some people drooping their heads. The derivative of natural log of x is 1 over x. So I get 1 over f of x times the derivative of the inside function, f prime of x. More commonly, this is written as 1 over y times dy dx. But it might be easier to think about this way. Equals the derivative of this, left d right plus right d left. Left d right plus right d left. 1 plus natural log of x. We're not done, we want f prime. Well, there's an f prime there, just multiply both sides by f of x, or y if you prefer. Let's use the f of x notation here, and we'll also use the dy dx notation down here. You can write the answer like this, and then simplify by replacing f of x with what it equals. It equals x to the x power. More commonly, you'll see it written like this. Dy dx is y, 1 plus natural log of x. But what does y equal? It equals x to the x. Either way is okay. It's more common to use that notation. This is probably less confusing. So that's a simpler example where logarithmic differentiation is used. Our example right here is more complicated. But it's the same principle. Take the log of both sides first. Log of both sides of this equation. Log of the left is just ln of a. Log of the right is ln of this thing. Then use properties of logs, not just the exponent one, but the product one. The log of a product is the sum of the logs. So you have the log of a product of two things here. That's the sum of the logs of each piece. And I did a second step here as well. I brought the nt down in front of this one. Now differentiate with respect to n, which is a little funny here, though, because n technically is a discrete variable. 1, 2, 3, 4, 5, 6, 7, etc. We don't typically think of having 8.27 compounding periods per year. But we could, if we wanted to. We could pretend n is a continuous variable. Then would be something we can differentiate with respect to. On the left, we need the chain rule, though, because a depends on n. You could replace this with a function name, if you prefer. 1 over a times the derivative of a with respect to t. I'm going back to partial derivative notation because we are finding partial derivative. 0 is the derivative of this with respect to n. There is no n there, and p does not depend on n. P, r, t, and n are all independent variables. 4 independent variables. They don't depend on each other. So you just get a 0 there. Over here, we need the product rule. There's your left function, n times t. Here's your right function. Think of t and r as fixed. N is the variable. Differentiate the left. Well, okay, if we do, I guess I'm not doing left d right plus right d left. I'm doing d left first. T is the derivative of nt with respect to n. Times the right function, plus the left function, but times the derivative of the right, and oh, it really makes me upset when it doesn't carry over my fraction symbol. There's supposed to be a fraction here. It shows up on my Mac, but it doesn't show up on the PC. The derivative of natural log of x is 1 over x. So we get 1 over the thing inside the logarithm times by the chain rule the derivative of that thing inside the logarithm as a function of n. As a function of n, that thing inside the logarithm can be written like this. When you differentiate that with respect to n, 1 differentiates to 0, this differentiates to, bring the negative 1 down, subtract 1 from the exponent. This can all be written as negative r over 100n squared after differentiation. And that's what I've got. It's just a matter of being careful. Now, in the rush of an exam, I would not give you an exam problem that's hard. Okay? In the rush of the exam, that would be too much, too easy to make a mistake. But if you've got the time to be careful about it, you can do it. Then this last thing is just some simplification. I canceled one of the n's, this n with one of these. I multiplied the 100n that was left through the bottom, and the minus sign comes out in front, and this term stays as is to get this. Okay, it's very complicated. Once again, showing you the power of differentiation in these rules. You know, I would not know about the answer ahead of time. I've got to figure it out. Let's interpret this now. This is more important in terms of what you should understand in a problem like this on the exam. I would not have you do a calculation like that on the exam, but I might have you interpret the meaning of these partial derivatives with linear approximation. So we're going back to linear approximation now as well. Let's use technology to find numerical values and interpret them. Here are some examples. Based on this fact, what is that fact saying? That's saying, remember, P is the first thing, that's 1,000 in this case. R as an interest rate is 8. I put a percent sign there just to emphasize that you're thinking of it as percent. Do not convert it to 0.08. I didn't have to put a percent sign there. N is 4, T is 10, and what this is claiming here is 1,000 times 1 plus 8 over 100 times 4 to the 4 times 10 power is approximately $2,208.04. It's how much your investment would grow over the course of 10 years. $1,000 investment at an 8% interest rate compounded 4 times a year for 10 years. It more than doubles. Let's evaluate the 4 derivatives from the other slides at the given point. I'm just telling you the answers here. Let's go ahead and show them all right away. The derivative of A with respect to P, for example, I use Mathematica to figure out it's about 2.208. I'll go ahead and show you how I use Mathematica here. On project 2, which is going to be due later in the semester, I'm not sure what day yet, you might need to use multivariable calculus functions in Mathematica, like I'm showing you here. Here's the formula. Notice f is a function of p, r, n, and t. I need to put them all in there with underscores for all of them when I define the function. And I can use Mathematica to do partial derivatives. The d function will do differentiation with respect to whatever letters over here. So this first one is the partial with respect to p. The second one here is the partial with respect to r. The third one is the partial with respect to t. And the fourth one is the partial with respect to n. That being the most complicated one. Have the computer do it, and I double checked it with my work. Numerically, what does this mean, though? You can plug in these numbers into the function to, again, confirm this number up here, 2208.04. That's how much money you have after 10 years. What does the derivative of this function with respect to p equal to at the given point? All this stuff just means at the point p is 1,000, r is 8%, n is 4, and t is 10. This turns out to be the 2.208, just like I have in the slide here. So I can have the computer do it, and I will put the Mathematica document in the folder as well. But again, let's just interpret the meaning of these things. That's more important. I probably should keep the numbers up there. T is 1,000. R is 8, N is 4, T is 10. The computer just confirmed the partial of A with respect to P, evaluated at P equals 1,000. It's really also evaluated at these other numbers too, but it gets too messy to show them all. It is about 2.208 dollars earned units of A, maybe earned is not the best word there. I'll go ahead and leave it though anyway because it'll help with the interpretation. You started with 1,000, so you actually earned less than $2,208.04. You earned $1,208.04 of interest. Let me just phrase it as dollars earned anyway. Per dollar of principal, dollar invested. So what does that mean? That would mean, for example, if you increased your investment by $1, if delta P was $1, you would expect your final amount to go up by $2.208 earned per dollar invested times $1 invested. Extra. Maybe adding the word extra in there. So multiply that times 1, that's going to be $2.21. If I deposit $1,001, I should expect that to be close to the balance. And here I've got Mathematica computing it for me. Notice I put 1001 in for B. Did it go up by $2.21? Actually, it did exactly. Because this is really a linear function of B. So the difference here really is exactly $2.21. And you can do the difference to confirm that. More interesting is the other derivatives, like with respect to, say, R. This one here. The derivative of A with respect to R, you evaluated R equals 8%. That says it's approximately 216.474. Dollars extra earned, or extra dollars earned, maybe that's better, sorry, per unit of R. What are the units of R? That's why I made the R be as a percent without converting to a decimal here, because you can call its units percentage points now. So, what's the approximate change in A? As R increases by, say, 1 percentage point from 8% to 9%? If I replace that with 1, I get an extra $216.47. It's an approximation. This one's definitely an approximation. It's not exact. Here's the derivative. The original function value. If I increase R, notice what changed here. Here R is 8%. Here I'm going to 9%. My balance increased by, it looks like $227 or so, a bit more than the estimate was. But it is an estimate, it's an approximation. It's a linear approximation. This kind of thing right here is a generalization of this equation. And generalizing that equation to partial derivatives. To find the total change in the amount, the final amount, take the rate of change times the change in R in this case, because we're talking about a derivative with respect to R. We're letting R change, not everything else. You can give similar interpretations to these other things. For the sake of time, I'm not going to do that. For the time we have remaining, let's go over implicit differentiation again. We went over this last time. It's the exact same example. I'm not going to get to the very last slide, but I think I may still assign problems related to the content of the very last slide. The very last slide is just a bunch of facts, a bunch of linear approximation facts and analogs for infinitesimals. You can derive these facts from the tangent line equations. We've done that before, actually. Okay? So I'm not going to go over that. I still probably am going to assign a few problems from that section. Okay? And I'll find a YouTube video, maybe Khan Academy, that'll give you some more details. But we have done it before. So what do I have here? I've got a function of two variables, a multivariable calculus function, x cubed plus y squared minus x. I'm interested in the curve in the plane where this function's output is always equal to 1. I'd like to know what that curve looks like for the purposes of understanding this function. And here's a visual of what's going on. So I'm putting the function in Mathematica. Here is a three-dimensional plot of it. As x and y vary over the plane that kind of goes into the screen, like this. The output, z you could call it, varies as well. The height of this above the xy plane varies. Since x, y vary over a plane, a two-dimensional plane, the graph is a two-dimensional surface inside three-dimensional space. Here's a more close-up view of its nature near the origin. Pretty cool looking, looks like a little seat that you can sit on there. It's got interesting features. For example, it's got a minimum right there, a low point. Right there, it seems like kind of an interesting point as well. It's a minimum in this direction, but a maximum in the other direction. Weird, but true. When you figure out where the function is constant, what you're really doing is you're slicing this graph with a bunch of different horizontal planes, where z is constant. And you can see the intersection of that horizontal plane with this graph is going to be a curve. Watch my finger here. It goes like this. Or if I change z, it could be in two pieces. There's a piece over here. And there's a piece in here. A curve of intersection. Contour plot in Mathematica can draw a bunch of those curves at once. There they are. This was where you sit right there. And this is where you put your legs over to the side, over here. We're interested in just one of these curves where the function output equals 1. It's this curve. I'd like to, for example, find its tangent line when x is 1. The point 1, 1 is on the curve. How do you do that? I showed you the implicit differentiation method last time. Let me show it to you again, but let me change my method slightly. Let me give the function a name. Let me call it g of x. Now this graph is not the graph of a function g of x because it fails the vertical line test. Plenty of vertical lines go through more than once. But near the point 1, 1, I could just focus on the top of the curve. And that would pass the vertical line test, ignore the bottom. I could call that function g of x. And what does it mean for this equation to be true? If y equals g of x, it means this is true. If you replace y by g of x, that's true. And since this is your expression for the function, I can rewrite this equation with g of x in place of y. And I'm wondering, where does it equal 1? And what is the slope of it at various points for x? Differentiate this with respect to x now. My goal is to find the derivative of this function at x equals 1. I want to find the slope of the tangent line right there. Take the derivative with respect to x. There's no more y's in there. This is more straightforward about what to do. The derivative of x cubed is 3x squared. The derivative of this thing, that's a chain rule problem. The inside function is g of x. That gets applied first. You don't know the formula for g of x, but that's okay. The outside function is the squaring function. Bring down that 2, plug in the inside function, then multiply times the derivative of the inside function. The The derivative of x is 1. The derivative of 1 is 0. Solve this equation now for g prime. Solve for that. Hang with me here. It's really important. So I need to isolate g prime on one side by itself. I should add 1 to both sides. I should subtract 3x squared from both sides. I get 2g of x times g prime of x equals 1 minus 3x squared if I do that. Now just divide both sides by 2 times g of x. G prime of x is going to be 1 minus 3x squared over 2 times g of x, or in dy dx notation, dy dx equals 1 minus 3x squared over 2 times y. Y is g of x, so these are equivalent. And now you can plug in your point. 1, 1. X equals 1, y equals 1. Into that formula, say the bottom one. You get 1 minus 3 over 2 times 1. That's going to be negative 1. The equation of the tangent line there turns out to equal that. The slope is negative 1. It goes to the point 1, 1. And that simplifies to y equals negative x plus 2. That's the equation of the tangent line right there. It looks about like that. And then you could use it to approximate the curve near x equals 1. And one of your homework problems is going to be approximating the curve like that. Okay? See you on the chart.